ma'am. This is Jainam Singhvi. Presenting my quantum mechanics project. Our project title is Ground State of Heisenberg Spin Chain. Um, Coming down, so this Heisenberg spin chain is a fundamental model used to describe interacting quantum spins in condensed matter systems. So this project, we are studying just a one-dimensional antiferromagnetic chain, Heisenberg chain, which consists of four particles with a spin of 1 by 2. We formulate the Hamiltonian using the Pauli matrices, and which is a 16-dimensional Hilbert space, and thus we get a matrix of 16 cross 16 order. Coming down to chapter 3, which I'm going to be presenting. So in the chapter 2, Mayank has calculated the Hamiltonian matrix, the 16 cross 16 matrix, which looks somewhat like this, the Heisenberg Hamiltonian matrix structure. Uh, in the second chapter. So yeah, this is the heat map structure of the matrix, where we can see it's a 16 cross 16 order matrix. Coming to the chapter 3, where we are going to be diagonalizing the Hamiltonian matrix, the 16 cross 16 one, and finding eigenvalues, eigenvectors, and using that to find the energy levels, the lowest energy levels. So looking at it, when we diagonalize the 16 cross 16 Hamiltonian, the following eigenvalue spectrum is received. So the supernode, it denotes the degeneracies. Uh, Coming down, these are the ground state eigenvalues. Lambda 1 is equal to minus 1.61, which also happens to be the lowest eigenvalue, giving us the lowest energy level. We get the eigenvector for this, which is this. For the triply degenerate levels, those are corresponding to eigenvalues 2, 3, and 4, which are equal to minus 0.9571. And these are the corresponding eigenvectors for those degenerate levels. Coming to another triply degenerate levels, which are the eigenvalues 5, 6, and 7, that happen to be minus 0.25. And this is the corresponding eigenvector. Coming to the non-degenerate level, which is the eigenvector 8, gives us the value 0.11. And coming to another triply degenerate levels, which are eigenvalues 9, 10, and 11, having the value 0.4571. Then comes the five-fold degenerate levels, which are eigenvalues 12, 13, 14, 15, and 16, which give us a value of 0.76. And the example eigenvector for this state is as mentioned. This is the table for eigenvalues and normalized eigenvectors of the four-spin Heisenberg Hamiltonian. So the 16 cross 16 matrix that we found out in the chapter 2 and 1. So yeah. So the eigenvalue 1 is the least eigenvalue in the entire table, corresponding to 1.616025. We are studying the physical interpretation of these ground states here. So as mentioned, the lowest energy eigenvalue of the Hamiltonian is comes out to be minus 1.6160, and this corresponds to the unique antiferromagnetic ground state. So being the lowest energy state, the isotropic Heisenberg model with positive coupling J greater than 0. So the interaction term comes out to be as mentioned these. They are minimized when the neighboring spins, they are anti-aligned, opposite to each other. So yeah, consequently the ground state is dominated by singlet-like superpositions, where the total spin of the entire system happens to be minimized. This behavior is characteristic of an anti-ferromagnetic chain. So yeah, then the energy is minimized when spin pairs, the local spin pairs, they form configurations and opposite orientations, uh, giving us a non-degenerate entangled ground state with total spin s that comes out to be 0. So yes, this was the key objectives of this chapter which I prepared on. computing all of the eigenvalues and vectors using numerical methods. Then coming down to identifying all the ground states, excited states, and energy gaps. Then we analyze the eigenstate properties and organized compute data for physical analysis in part 4. So yes, the next part is to be continued by Akshay. Thank you.